To the? That's correct. And what if more people arrive and the ground floor is already full? In what floor they should go next?
Second floor.
That's correct. And how about if the ground floor and second floor is already full? Where the next people go?
Third floor.
That's right. We fill the lower floors before the higher floors. Why do you think we do that? Anyone? Carl? You have an idea? Good idea. How about Mary? Why we fill the lower floors before the higher floors? Very good. And we fill the lower floors before the higher floors because it is closer to the entrance, like easiest the floor to reach. You understand, class? Again, what happens when the lower floors and is already full? The next people will go to the instead of people, we have tiny particles that move inside an atom. What do you think these tiny particles could be? Yes, JC. That's right. And today we will learn how these electrons move inside an atom and how they occupy different spaces and levels and how this arrangement affects the elements we know. Now, take a look at the electric fan. The blades moving or spinning too fast. Do you see each blade clearly?
Oh.
Okay. We just see a blur, right?
Yes.
And that blur is like an electron cloud. It shows where the electrons most likely to be found. The electrons moves very fast that it forms a blur or a cloud. Since the electrons move too fast, we can pinpoint the exact position of the electrons. Now, so what can we say about the movement of electrons? Do you think they move in fixed paths?
No.
Very good. How about in regions? Do you think they move in regions? Who says yes? Raise your hand. Who says yes? Do you think the electrons move in regions? Who says no? Actually, they move in region. And these regions are called orbitals. Each orbitals have different spaces and levels. Even though the electrons don't move in fixed paths, we can still describe where the electrons most likely to be found. Where the electron most likely to be found? In the electron cloud. Very good. These orbitals are not all at the same number, are not all at the same distance from the nucleus, just like our building. Each floor represents the energy levels. Now, which floor we filled first, the lower floors or higher floors?
Lower.
Very good. And those are lower energy level. Filled first because they are closest to the nucleus. And like easiest floor to reach. How about the electrons farther away? Where do they stay? In lower floors or higher floors? That's right. And that is the higher energy levels. Farther from the nucleus with more space for electrons. Now, class, do you think each floor can hold the same number of people? formula, 2n raised to 2. Now let's try in the first energy level. 2 and n is the energy level and raised to 2. So 1 times 1, because it is raised to 2, is equal to, and 1 times 2 is equal to 2. So the maximum number of electrons in first energy level is 2. So how about in second energy level? Can you solve it in the board? Not C and 3. And third energy level, Cedric. And for the fourth energy level, Cedric. Fourth energy level. Must you get the same answer? Very good. Now, what do you notice from the maximum number of electrons to first energy level, from first energy level to fourth energy level? What do you notice? From the maximum number of electrons of first energy level to fourth energy level? Yes, sir.
The maximum number of electrons.
That's correct. The higher the energy levels holds more electrons. Now, these orbitals are in each energy level there are called sub-levels. So, as we move to the periodic table, the electrons fills these levels one by one, starting from the lowest energy level to the highest energy level. And now let's see how these electrons are arranged inside those levels. And this arrangement is called electron configuration. And each energy level, there are types of orbitals called sublevels. And these sublevels are presented using the letters S, P, D, and F. So as you can see in our periodic table, the period number is also the energy level used by the elements in that row. So this is the first energy level, second energy level, third energy level, and so on. And the S block is located in the left side. In what group they are located? In what group they are belong? Yes, miss? Very good. How about the P sublevel? In what group they are located? They are from what group? The P. Yes, Melody. That's correct. And what type of orbital or sublevel does the middle part or the transition metals? Yes, Zian. And what type of orbital? What is this our sublevel here? Letter E. Very good. And how about the blue rows below? What type of orbital or sublevel? of these three orientation? So we have 6. Yes, very good. In P sublevel, we have the maximum number of electrons, which is 6. And in D sublevel, or in D room, we have 5 orientation. So how many people can stay here? Yes, Mark? Very good. And D sublevel, it has a maximum number of electrons, which is N. And how about in F sublevel, where in our F room, it has 7 orientation. How many people can stay there? 7 orientation.
14.
Yes, that's correct, Miss. The F sublevel has also 14. And in the easiest way to get the maximum number of each sublevel, we can count the columns in the periodic table. For example, the P sublevel. How many columns are here in our P sublevel? And it is the same with our table. You understand, class? And as you can see in our building, the first energy level has the S, second, which is SP, third, SP, E, and fourth, we have S, P, E, F. And if we add all these sub-levels, we can get also the maximum number of electrons each energy level. For example, in second energy level, what is the maximum number of in second energy level? Energy level. Using the formula here. We have A. So if we count these rooms or sub-levels, we have S room 2 plus the P room 6. We have A. So same with this. Do you understand, class? Now, let's try to write an electron configuration of elements. This is the electron configuration of hydrogen. 1 for the energy level, S for the type of orbital, which is S, and superscript 1 for the number of electrons in the orbital, which is the S. Do you understand, class? Now, let's try to write the electron configuration of helium. In what energy level does helium align? Very good. And what is the type of orbital is available in the first energy level? That's correct. And how many electrons does 1s can hold in helium? Very good. So this is the electron configuration of helium. Now, let's try to write the electron configuration of oxygen. Just like our building, we fill the lower floors before the higher floors. And in writing our electron configuration, we will write all the type of orbital and their number of electrons from lower energy level up until the elements that we are writing. So, we will start first in the lowest energy level. So, what is our lowest energy level? What is our lowest energy level? 1. And what type of orbital is available in first energy level? And how many electrons does 1s can hold? Very good. Now, let's proceed to the second energy level. So what is our energy level now? And as you can see, there are 2 types of orbital now. And we will start from left to right. So what type of orbital we will write first? the 2s can hold how many electrons?
2.
Very good. So now, let's proceed to the other type of orbital. So what is our energy level? We'll just proceed here. So what is our energy level? Energy level.
6.
Yes, very good. And what type of orbital? D. So, how many electrons can 2p can hold until the oxygen?
6.
Until the oxygen, here. Can you bring us your periodic table? Yes, in 2p only. We have, can you bring out your periodic table? Yes? Very good. We only have 4 electrons in the 2p because this is the oxygen. And we already write all the number of type of orbital and number of electrons of the other electron configuration. Do you understand, class? Saba? Okay. Now let's try the 4. Because in first energy level, remember, we have a type of orbital which is S, and we have how many electrons? 2. And in the second energy level, and 2s, how many electrons? 2. And in 2p, and the basement or the oxygen is here, we will just count the number of electrons from the p sublevel. So we have 1, 2, 3, 4. Do you understand, class? So now, let's try the carbon. Yes? Because we are writing the electron configuration of oxygen. You understand, class? Now let's have another example. Let's write the electron configuration of carbon. So we will write all the type of orbital and number of electrons and their number of electrons from the lowest energy level up until the element that we are writing, which is carbon. So let's start with lowest energy level. What is our lowest energy level? 1. And what type of orbital is available and good. And how many electrons? 2. Right. Now let's proceed to the second energy level. What is our energy level now? 2. And what type of orbital? We will write first. We will write first. We will start from left to right. And how many 2s electrons can 2s hold? 2. Now, let's proceed to the P. So what is our energy level? 2. And what type of orbital? P. Now count the number of electrons until the carbon. Very good. Do you understand, class? Yes. Now count the superscript of the oxygen. The electron configuration. We have how many electrons? Here in oxygen. Oxygen. 8. And what is the atomic number of oxygen? 8. Yes. So if we add all the superscript or electrons, we can also get the atomic number. It is equal to the atomic number. Do you understand, class?
Okay, now let's try to the next electron configuration of this manganese. So since we already know the maximum energy of this level, so what are the types of One S2, two pieces, and the next is S. And the next class, what is it? Yes? 3P. 3P6. So, then 3P6. So, and the next is for S22. And the last is because it's n minus 1. Yes. Remember D? Remember D?
Yes.
This one. So, how many electrons do we have? Guys. Anyone from the class? Yes, Natalie, Dasha. How about Ishra? How many electrons do we have on this electric configuration? Is 25. 25. Very good. So what is the atomic number of the manganese?
25.
Very good. So next, let's try the electric configuration of the machine. So Samario, since let's have we will refer to the photo of the mini table. So look at this formula n minus 2. So we subtract the number of electrons on each sub level. So now how many what is the type of orbitals in the inner number of electrons in the so okay, sorry to make this easier. In the noble gas, we choose the number of the 7, which is the to get this electron configuration. We choose the noble gas, the 7 form. We use the noble shorthand gas. Remember. this shows is difference of salt levels. So this is okay to help you remember is mnemonic. So to help you is to remember how to use the mnemonic. So okay, here's what we got. So si Sunny pumasok sa pinto, si Danny pumasok sa door. So paano si Francis Danny, paano si Francis Danny, paano? Okay, do you understand that? So help you remember this pattern. So okay, you see mnemonic. So look carefully at the first level mo. 1S or 2S? 1S. Very good. So the next is, what you want from the back? S. And so that's the key. So that's the key idea of electrons. So always will be lower energy, lower energy sub-levels first before going to higher ones. And last, how will so last? Very good. So that's why we use the diagonal pattern that shows us which there's some level to fill flex energy electron configuration path to be building up to this pattern. So is that clear, class? So now the previous example the oxygen. So So, will you read the definition of the valence electrons, class? Will you read, everybody read the definition of valence electrons? Okay, very good. So, valence tell us how many electrons an atom is produced or being to become stable, just like the noble gases. Noble gases. So, is that clear, class? So, now let's try another example. Let's try another example to see if the same idea applies to other elements. So let's look at samario. So its electron configuration is 6s2 and 4f6. So which energy level has the highest number? 6. So what is the so how many electrons